Okay, so a theorem. Um, okay, so if S is greater than n over 2, then HSRN is an algebra with respect to the product of functions. Okay, that's it, functions. That is that if f and g are in Hs of Rn, then f multiplied by g is in Hs of Rn with well, the norm of f multiplied by g s2 is less than equal than cs f s2 g s2. Okay, so we're asking high regularity is greater than n over 2, and it will be an algebra. So to prove this, you can see with the uh, triangle inequality the following uh, inequality. Okay, this bound, just adding and subtracting eta and making some calculations, you have that this is less than equal than 2 to the s 1 plus psi minus eta squared is 2 plus 1 plus absolute value of eta square is over 2. Okay, so this will be important. So if we consider lambda s ffg, that will be equal to 1 plus psi squared s over 2 multiplied by fg, let's say transform. Okay, so this will be equal to 1 plus psi squared is over 2, and now recall that this can be the convolution of transforms, and so here we will have to multiply by the absolute value of the integral in Rn of f transform psi minus eta, this is an eta, g transform eta, the eta. Okay, and now using this, we can bound this integral. First we can bound this integral just putting the absolute value inside. This doesn't depend on eta, so it can go inside, and we can bound the whole as an integral with this, obtaining the following. So this will be less than equal than 2s integral of Rn 1 plus, well, this, we will have eta c minus eta squared is 2 multiplied by this, but now it has the absolute value inside, so we will have f transform psi minus eta g transform eta. So now we close, and now we have the other term, and that will be plus so 1 plus eta squared, okay, s over 2, and now again multiplies this. So f transform psi minus eta g transform eta, and now we can close all this d eta. Okay, so we have this bound, and this can be bounded again because now we will have let's say 2s multiplied by, well, lambda s f, and now you can see here we have psi minus eta and psi minus eta, and we have uh, uh, the definition of lambda s of f in this case, convolution g transform, and plus, and now we have the other way because now we have the definition of lambda for j or for g. So we will have f transform convolution lambda s g. Okay, so now if we take the L2 norm and we use the Young's inequality for convolution, we will have that f multiplied by g of s2 is equal to lambda s fg. That is how we started this bound, and now we will have that this is less than equal than a constant c multiplied by, well, lambda sf, but now is norm 2, and Young's inequality tells us that this has to be in norm 1 plus, well, the other way around, f transform is in 1, and lambda now of gs is 2. Okay, so recall that we proved in the last video that f transform norm 1 is less than equal than cs f s2. Okay, and this is if s is greater than n over 2. Okay, so knowing that, we can say that the norm fg s2 is less than equal than a constant cs. Okay, and let's suppose now that to have this, now we will have another variable, and let's call it r is greater than n over 2. So cs is this is greater than cs multiplied by f s2. Okay, as we have it here, and g transform 1 plus f1. Okay, and now this is gs2. Okay, and this will be less than equal, now yes, using this and this, then cs f s2 g r2 now. Okay, using this plus f r2, now bounding this, and g s2. Okay, so if we make now s equal to r, okay, then we will have that fg s2 is less than equal than, well, we can say 2cs, this is another constant, fg, and both in norm s2. Okay, that is what we wanted to see. Okay, so finally a definition um, let omega be an open subset of Rn. Okay, so we say that f from omega to complex numbers is in hs log of omega, okay, with s greater than 0, if for every psi c infinity naught, okay, recall infinity derivatives and support, we have yes, compact support, I wanted to say there, we have that psi f is in hs of Rn. In other words, if omega prime is included in omega, then f restricted to omega prime coincides with some element of hs in Rn in omega prime. So, for example, um, if n is equal to 1 or um, and let's say that f is equal to x, then well, then f is in hs log. That means that is in hs log for every s positive, uh, and for every omega in R. So that means that you can multiply this f with any psi in complex support infinite derivative, and you will always get that this multiplied by x will always be in hs, that is, to be in hs log.